Hi, I'm Xingyu, and I'm excited to introduce our work, Frequency-Aware Self-Supervised Monocular Depth Estimation. The depth estimator takes a single RGB image as input and outputs its pixel-aligned depth map. We start with the first problem here. When training gets to the middle part, on most objects, loss only appears on the object boundaries. If the prediction is wrong, loss should have appeared on the concentrated parts. So where do these losses come from? If we enlarge the image patch multiple times, we can see that one pixel characterizes the color of two objects. The photometric loss makes no sense, as no objects would match these colors. Second is their locations. When projecting these pixels to 3D point clouds, they appear as noise outside the real objects, regardless of their predicted depth. To overcome this limit, we propose ambiguity-masking. The ambiguity map pixel-wise multiply with the photometric error to simply filter out these pixels. And then we get the final loss. In particular, we first extract the EO pixels in target image and source images. Then, we bilinearly sample AT plus N to get which pixels in the reconstructed image are from the ambiguous pixels in the source image. We take pixel-wise maximum, because for each pixel in the loss map, ambiguity from either source image or reconstructed image can both cause its loss to be untrustworthy. Before introducing the second problem, we first define what is an absolutely fair loss. In short, given the loss function, the more accurate, the smaller the loss is. Take the loss function in one of the supervised depth estimator, for example. This is a typical absolutely fair loss because the loss is proportional to the prediction error. We show problem 2 here. The loss function used in self-supervised depth estimation is the photometric loss as defined here. To demonstrate the problem, we focus on the white pixel in the left view. The losses for different predicted disparities look like this. If we consider these two disparities, the red one has the maximum photometric loss, while the orange one has the minimum. However, the red one is closer to the ground truth, which means it's more accurate. This non-proportional relationship indicates that the photometric loss is unfair, because the poorer disparity instead has a smaller loss. What's worse, loss of the ground truth is even larger than that of some incorrect disparity, which means the network has the wrong global optimum. To alleviate this problem, we present auto-blur module. Augmented with auto-blur, as the yellow curve shows, the loss function becomes more stable. Most importantly, it becomes fair, in which the more accurate, the smaller the loss is. Last but not the least, loss of the wrong global optimum gets increased, preventing it from deceiving the network. Our methods are highly generalizable, helping a large number of sort-out methods to achieve better results. Thanks for listening. Paper and code are available on GitHub.